The last type of problem that you'll see in the online homework for section 1.2 has to do with just reading what are called piecewise functions. These piecewise functions are really common in applications in calculus and algebra because it's not uncommon that we would describe a function's outputs using different rules depending on which input is being used. I'll show you an example of that in a second, but for right now, let's see if we can read the notation. The most challenging thing is that the standard notation, which you see here, is written sort of backwards. You can see the two rules over here for the outputs, and then of course when we have multiple rules we have to know which one we're supposed to use at which time, and that decision is made over here. So we first have to decide which rule to use based on the stuff on the right, and then we have to plug the number into the appropriate rule using the thing on the left. So your eyes will track from right to left as you're deciding how to evaluate one of these functions. So for example, if I have f of -2, then I'm going to look up at the conditions that I've circled under the number 1, and I ask myself which of those conditions is satisfied by the number -2. And I can just try -2 in for x in each of these things that I've circled here in number 1. -2 is less than 0, so that indicates that that first condition is satisfied. Notice that the second condition is not satisfied. That will always be the case, that any given input will only satisfy one of the conditions on the right-hand side. So because -2 satisfies the first condition here, then that tells me that I should use this output rule for that input. And so I'm going to apply the rule x minus 4 using x equals -2. So there is my evaluation. The -2 goes in for x in the first output formula. Contrast that with the input number 1. When the input number is 1, the first condition, it's circled over on the right, the first condition, x less than 0, is not true. 1 is not less than 0, but 1 is greater than or equal to 0. So the number 1 satisfies the second condition, so I would use the second output formula for evaluating the function. And then finally, f of 4 also satisfies the second condition. 4 is greater than or equal to 0, so f of 4 would use the formula x squared instead of the other formula. So the only thing weird about it is that you have to check the condition on the right to know which piece to use, and then once you've made that decision, you're still just plugging into the appropriate algebra formula on the left. We can graph these things too if we have enough points, and in this example I'm just going to do a couple of evaluations for practice. If you want to pause the video here and see what you think for the values given here, f of 1 and f of 3, that would be a good idea, and then I'll show you what the graph looks like. So here are the 2 points evaluated. F of 1 will be 1 squared, because that's using the formula for the first part of the piecewise function, and f of 3 is going to be 0.5 using the second piece of the piecewise defined function. And I plotted those 2 points on the graph. We can see that the definition of the piecewise function has a transition at 2. So the one part only goes for x is less than 2, and the other one for x greater than or equal to 2. And so we know that with the x value of 2, I'm just going to write a very faint dashed line here. The line is not part of the graph. I'm just trying to illustrate what's happening. That at x equals 2, the graph is changing its behavior. The function is changing its behavior, so we expect the graph also to change its behavior. So just for an exercise to make sure you're doing all of this right, if you want to pause and evaluate several more points, both on the left side and the right side of that line, even some fractional points, then I'll take a breath and I'll fill in some of the points too so we can see what it looks like. So here are my points. You can see that over on the left side of x equals 2, the points are kind of curving upward, and on the right side they're falling on a straight line. But those are just me plotting some points on the left and the right side. One way this comes up a common example is the example of taxi cabs in a city. This problem refers to Uber rides, but Uber doesn't really do exactly rides based on mileage. It uses some other factors as well. So this is just a simplified kind of function where we have one flat rate for rides up to a certain amount of distance, and then after that, you start having an additional charge for every additional mile. So that's fairly common with city cabs, and Uber does something like that, but it has a lot of other factors as well. There is one typo on this slide. This should be here. Well, I'll just change the whole thing. It should be the 6 mile flat rate plus $2 for every mile beyond 2 miles. So it should look like this. And under that model, we can interpret this. This would be the cost of a 1 mile ride. And if you read the paragraph, a 1 mile ride should cost $6. Everything under 2 miles costs the same rate, $6. But C of 3 should cost the $6 plus $2 for every additional mile, and the additional miles would be 1 additional mile. So a 3 mile ride would be $9. So in this case, you can see that the two rules are related to each other. They both are cost of the ride, but there's a different formula, different output formula that's used for values of x less than 2 and for values of x greater than 2.